Get started. Hello, everyone. Thanks for joining us today. My name is Danica. I'm with 3C Rent in the county of San Luis Obispo, and welcome to What Energy Consultants Need to Know About Quality Installation, also known as QII, with our instructor, Russ King with Coded Energy. And next slide, please. Before I pass things off to Russ, I just have a few logistical slides to go over. A few quick Zoom reminders before we get started. Please make sure you're on mute throughout the duration of the training. And we highly encourage questions. And if any questions do come up, feel free to put them in the chat or you can raise your hand and we can unmute you. This session is being recorded, which will be shared with you along with the slides in the next few days. Next slide, please. So just a little bit about who we are. We are the Tri-County Regional Energy Network, also known as 3C REN. We are a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura counties. 3C REN is funded by ratepayer dollars collected through the public goods charge found on our utility bills. And the benefit of being ratepayer funded is that there's no cost to those we serve, and we are able to bring those dollars back into our region. Next, please. Next slide, please. 3C REN currently offers 6 programs focused on 3 services: incentives, training, and technical assistance. Our training today is part of the Energy Code Connect program, and you can find additional trainings and learn more about our other services by visiting our website, 3c-ren.org. And with that, I'll pass things off to Russ to get the course started.
Hope you have one more slide, though.
Oh, we can go to the next slide.
Okay. Awesome. Cool. Thanks, Danica. Good morning, everyone. Thank you for joining us today. My name is Russ King, and my company is Coded Energy, and I've been doing this for a little while. I helped write the very first QII handbook for CalCerts. When the QII first started, I was training HERS raters back then, and boy, that was a fun time. QII was quite an interesting thing to require of builders at the time. I think it's been around long enough that most builders have kind of figured it out, but there's still a lot of interesting things, the little corner cases and things like that that need to be addressed on occasion. But the bottom line is still the same. In order to pass QII, you really need a lot of coordination. People have to coordinate. You can't just throw insulation at a house and put it in correctly and expect it to pass. It's got to start with the design of the house, okay? And so that's what we're going to talk about today. So just some real basic facts. It's a lot harder to make a house comply to the code than it ever was. It's just that the energy code gets more and more strict every code cycle. 2022 was particularly tough. And what that means is that you have to look for more opportunities to get extra credits and things like that. And the only way to really get extra credits is to use the performance approach, which is, in new construction, that's 99.999% of all new homes use the performance approach. But by using the performance approach, there's some extra credits you can get. But there's also some prescriptive measures that are sort of assumed to be on the house unless you choose not to model them. And that's basically what QII has become. It used to be an extra credit, okay? It used to be something you could go above and beyond and use QII, but now it's not. Now it's assumed to be on the house. It's on the house that you're being compared to. So if you say, well, I'm not going to do QII, well, then they derate your house compared to the house that you're being compared to, and that's a big hole you have to dig out of with some other features. And those other features are getting harder and harder to come by. So even though QII is technically a prescriptive measure, it's really difficult to model it away. Okay, obviously that depends on your climate zone, and certainly in the 3Z Ren climate zones, it's not as hard as say as it would be over in the Central Valley or something like that. But it is not easy to model it away. All right. So it's a very, very common measure in new construction. So you just kind of assume it that it's there for most cases. Okay. Um, and where that really becomes a big issue is if for some reason they fail QII. All right. And sometimes when they fail QII, it's really, really, really difficult to fix it. Okay. To make it so that it passes. All right. And so a lot of times what happens then is the energy consultant has to go back to the energy model that they use to demonstrate compliance, remove QII, and then try to make the house pass without QII. And that can be extremely difficult. Okay. It's not impossible, but it can be very difficult and very expensive. Okay. And the reason is that one of the main reasons that QIA fails is because they sheetrocked over the insulation before the HERS rater saw it. All right. That's an automatic fail. Okay. The only way to fix that is to remove the sheetrock, and that simply isn't going to happen. Okay. That's just way too expensive. And so what they then start looking for, and remember that the house is sheetrock, so it's pretty far along. They start saying, well, gosh, can we install a more efficient water heater? Can we install a more efficient air conditioning, heat pump, whatever? Can we add more insulation in the ceiling? You can't change the windows because those are already installed. Maybe put a battery on it or something like that. So it becomes very, very difficult. And so for your climate zone, you just kind of need to play around with some models. If you have some models, energy models that you've done where the house has QII on it, um, and it passes, remove QII and see how big of an issue it is. See how much your compliance margins change by, and then see what it takes to get that house to comply without QII. Okay, very interesting experiment to do. All right, and so bottom line is, some of these HERS measures can no longer be modeled away if they fail inspection. And QII is certainly one of the more important ones. Okay. All right. So, the other thing too that's very, very important that I just see way too many energy consultants do, and by the way, I'm on the KBEC board of directors. KBEC is the California Association of Building Energy Consultants. They have the voluntary certification program for certified energy analysts and all that good stuff. And my very first job out of college, way back in 1988, was doing energy calculations. So I've been doing it a while. I don't do a whole lot of energy calculations these days. I mostly do HVAC design work, but um, one of the things I've noticed with energy consultants is that a lot of energy consultants kind of work in a vacuum. Somebody sends them a set of plans, and they model it, and they get it to pass, and they send it to the architect, and it gets uploaded to the registry and all that good stuff. And then they just kind of forget about it. They're just like, okay, I'm done. I don't have to worry about it anymore. And that's not the right way to do it. Okay. And I really, really encourage energy consultants to be much more involved, and of course to be paid for their work properly too. Okay. I'm not saying do all this extra stuff for free, but charge a little more and be a little more involved in the project, and that'll just make everybody's lives easier. Okay. And the QII is a great example of why you should do that. Okay. And so, the other thing too is that when you're running the software, whether you're using Energy Pro or CBEC Res or any of those, and you run it and just kind of I'll date myself. When I was doing energy compliance work, I was doing it on a computer that didn't even have a hard drive. All right, it had floppy disks that you had to swap back and forth. And when you built your house and you ran it, it took over an hour for that simulation to process through. All right. And so you would spend all morning, you'd get your house into the software, and you'd hit run, and it would just start clicking away. January, February, March, and it would just go through the years, and it would took over an hour. So you'd go to lunch, and you'd come back, and you'd still have to wait a little while, and then your computer would ding. And the old software I used was MicroPass, it was called, and it would go. And if the house passed, it would go ding ding ding, but if it failed, it would go ding ding ding. So it'd give you this sad ding sound if it didn't pass. And so if it went ding ding ding, you would, oh cool, it passes, and you would see what features it took, and you'd send that to the architect, and off you go. But if it didn't pass, you had to make some changes and run it again. and then it was another hour to get it to run. All right. So it's very, very tedious. But nowadays, you lucky people, it'll run it in seconds, right? You hit run and oh, it does the calculation in seconds. Okay. And there's a downside to that because you don't have to, if you run it and it doesn't pass, and you change something, you run it again, it doesn't pass, you change something, you run it again, it doesn't pass, you change something, you run it again, it passes. All right. You haven't really thought too much about each one of those things that you did potentially. All right. And so what I like to say is don't check a box and just say, "Oh, wow, I checked a box and it passed. Well, look at there. That's off we go." Know exactly what it means when you check that box. And QII again is a great example of that. If you check the QII box, and remember this used to be extra credit, and people would just come in and check the box, and it was a big deal. Now it's more common, so it's not that big of a deal. But other things like oh, what are some examples? There's little boxes that you check, whole house fan or with ventilation cooling. You just check a little box and all of a sudden it passes. Well, what exactly does it mean when you check that box? Okay. Well, that's what we're going to talk about specifically related to QII. So, energy consultants need to communicate the potential costs and requirements of each HERS measure they specify. All right. It is very important that an energy consultant have a good idea of how much things cost. In order to be a good energy consultant, your job is to tell an architect or a builder or a homeowner, whoever your client is, what it takes to pass the energy code for the least amount of money, the most cost effective way to pass the energy code. You can get a house to pass. There's hundreds of different ways to get the same exact house to pass the energy code with all different kinds of features, and some of those packages of energy features are way more expensive than others. All right, so it's good for an energy consultant to know not just the what features are in the house, but how much they cost. Okay, just as important, it's it's important that the energy consultant knows what it takes to pass certain features. Okay, if you say, "Oh, we're going to run high efficiency equipment," well, then that triggers HERS verification for verifying the efficiency of the equipment that got installed. And some people think, "Oh, that's just a matter of going out and looking at the labels and say, oh yeah, it's a 18 SEER or whatever." Um, and just checking the efficiency that way. But it's actually quite a bit more involved than that. You got to go to the AHRI directory. You have to make sure that the condenser, the coil, the air handler are all a match set. That combination has been certified by AHRI. You have to be able to print out those certificates and all that good stuff. Okay. Um, and QII is again an excellent example of that. It's very easy to check a little box and say, "Oh, let's just do QII." And I distinctly remember, back when QII first started, we'd have installation contractors would call us up and say, "Hey, what is this QII, anyways?" And we say, "Oh, well, it stands for Quality Insulation Installation." They go, "Oh, quality. That's our middle name. We know what to do." And they would just assume that they have to just do a good job installing the insulation. Well, it's a lot more than that. Okay. It has to do with the air barrier and defining the thermal boundary of the house, and there's a lot goes into the design of the house, not just how the insulation is installed. Okay, so when you specify a HERS measure, any HERS measure, it's really a good idea to send them the protocols. Okay, the protocols are what the HERS rater is supposed to follow when they inspect a particular measure. Okay, it's reference appendices. Go to table RA2-1 in the reference appendices, the 2022 reference appendices. Go to table RA2-1. It will list all the HERS measures and then the sections of the protocols for inspecting those things. Okay. And QII has a huge one. All right. It's just many, many pages. But I like to think of those as the answers to the test, right? If one of the requirements is duct leakage testing, all right, and the HERS rater is required to follow certain protocols when they test the duct leakage, then the installing contractor looks at those protocols and they go, "Oh, okay, well, this is what we have to do to pass the test." It's like having the answers to the test. Then they just have to do that thing so that the HERS rater, when they test it, it'll pass. Okay. Same thing for QII. So the protocols, super useful, super important. Okay. And by the way, the protocols, HERS raters are required to follow the protocols. The protocols are what help ensure consistency between HERS raters. So if you have 5 HERS raters go out and inspect the same house, hopefully they all come up with the same answers. All right. Now it's not a perfect world and things happen, but it's the protocols that you fall back on. Okay. All right. So, QII is a protocol for the verification of properly installed insulation. Okay. Well, QII stands for Quality Insulation Installation. It is a protocol for the verification of properly installed insulation. It is not a protocol for installing insulation. It is a protocol for verifying properly installed insulation. Okay. And I can remember when QII first came out, we had a lot of people going, "Who comes up with this stuff? Who invented this? Who made this garbage up? Blah blah blah." They were all upset about it. Well, guess what? Nobody made it up. It comes from industry standards. It is based on existing industry standards. So there's big organizations like NAMA, North American Insulation Manufacturers Association, and ICAA, which is the Insulation Contractors Association of America. Those are big associations in the United States that set standards for how insulation should be installed. QII is based on their standards. Okay. This is not something that the Energy Commission folks made up or some energy consultant made up. This is stuff that the industry, the manufacturers came up with in order for their insulation to work correctly. All right. They came up with this, and then QII is based on those standards. All right. So the verification then is delegated to third-party special inspectors called HERS raters, which, by the way, they're changing the name. Next year, they're going to be called Energy Code Compliance Raters or ECC raters, just so you know. And the entire protocol for QII is in section RA 3.5. All right. So if you just, you know, download the reference appendices, pull it up on Adobe Acrobat or whatever, and just pull out that section, RA 3.5, you have pretty much everything you need to know about QII. All right. Except that it's kind of written in Cody language, right? It's not super useful and it doesn't cover all of the details. And so what we did a long time ago is we took RA 3.5 and we turned it into a book, okay? And it's called the CalCerts QII Handbook. We added a whole bunch of pictures and diagrams, and we added example and stuff like that. So it is sort of a supplement to the reference appendices, okay? Um, but the RA 3.5 is certainly if that's what you fall back on. That is the code. RA 3.5 is the code, and that's what you fall back to. The QII handbook is just sort of an enhancement of that. Okay. It is not code language, just so you know that. Okay. Um, let's see. So, the QII Quality Insulation Installation, which by the way is a horrible name, is a tongue twister if there ever was one. That's why we just call it QII. It is a prescriptive measure. That means it is assumed to be on the house unless you take it away. Another way to think of it is it's on the house you're being compared to. The house you're being compared to is based on the prescriptive measures. So it has QII on it. And when you run the energy compliance software, it creates a score, if you will, for the standard house, which is the house you're being compared to, the standard house. And then you have your proposed house, and it does an energy simulation of that one, and it comes with the scores on that one. And then you compare those two houses together. So this house becomes your target. And if this house has QII on it, it's going to have very low energy use. And if your house doesn't have QII on it, well, you've got to still bring that energy use down so that it meets that house that does have QII on it, but you're going to be using different measures. Okay. And that's what I was saying earlier. It can be very difficult to do that depending on your climate zones and things like that. Okay. There is an exception for additions. Prescriptive additions of 700 square feet or less do not need QII. All right. And like I said, it used to be an extra credit prior to the 2022 or was it 20, maybe it was the 2019 code, I think, when it first became a prescription rate. I can't remember, but it used to be an optional, it used to be just extra credit. And so you would run it, you were being compared to a house that did not have QII. Okay. And then you say, oh, I can't, I'm not passing. I will add QII to my house to make it pass. Okay. And back then, it wasn't nearly as common of a feature. And it was probably the single highest uh, failing HERS measure of all of them by a long shot. Yeah, it had like a 75% fail rate on the first inspection. But now it's much more common in new construction. Insulation contractors are more familiar with it. They've gotten more, they figured out how to deal with it basically, and so it doesn't fail quite as much as it used to. Okay. Let's see. So if you go to Energy Code ACE and search for decoding QII, I think that's still the name of it. If you go to their recorded trainings and stuff like that. Gina Rod and I teach a class about QII, and they have a handout. And if you can find that on the Energy Code ACE handout, there's something attached to it called the QII handbook. Okay. Um, and excuse me, I tickle my throat. Um, the as you all probably know, CalCert's closed its doors last year, and so the CalCert technically the CalCert's QII handbook is no longer available, but it was always a free PDF download and everything like that. So it's floating around out there all over the place. So you should have no trouble finding it. And I've actually been asked to kind of rewrite it. So hopefully that's a big project I have to do before the end of the year. It'll be um, updated for the 2025 code, which there's not going to be a whole lot of changes, but we will put out a new sort of handbook. I'm not sure what we're going to call it yet, but it'll be sort of take the place of the old CalCert's QII handbook. So keep an eye open for that. But for now, you should be have no problems finding the CalCert's QII handbook floating around out there. And a lot of the images and diagrams from that handbook are used in this training. Okay. So, QII, W2EF, and of course that stands for why the fuss? Well, there was a large study done prior to the 2005 Energy Code. The Energy Commission contracted a bunch of consultants and said we're trying to figure out what is industry standard for how insulation is installed in California. Is it good? Is it bad? What is the current state of the industry and how insulation is being installed? All right. And the result was it's terrible. It's really bad. It is, it is, it is, every single house they looked at was bad. Let me put it that way. So they basically said, okay, fine. If that's just how it's going to be, if that's just how houses are going to be, they're going to do a bad job installing insulation. Well, then heck, we're not going to give them full credit for that insulation. They calculated that it was being installed so poorly that it results in about a 13%, 13.5% reduction in R value. Okay. So they said, okay, fine. But well, if that's how it's going to be, then our software, when we model insulation, we're going to derate it because that's every single house we looked at was that bad. Okay. Well, of course, then when people got wind of this, they were like, "Oh, wait a second, that's not fair. I mean, you can't just assume we're going to be guilty." But the study proved that everybody was guilty. So it was a fair assumption. But heck, let's give people a chance. Let's give people a chance to not do a bad job. Let's say, okay, well, if they really, really want full credit for that R value, then we have to make sure that it's installed correctly. And so they came up with the QII protocols. And it has to be third party verified by a HERS rater. So that's how QII started. That's how it came into being. all right, was as a way to not get penalized. All right. Well, as time progressed and people got better at it, industry got better and better, better. And now it became a prescriptive measure, and they just said, okay, now we're going to assume that you are going to do a good job, but if you choose not to do a good job, we're going to penalize you for it. Okay, so it's kind of flipped, but that's a good thing. That shows that the industry has improved and they are doing a better job. Okay, so here's the deal: if you don't plan for QII from the very beginning, there's going to be headaches. There's going to be problems. Coordination is key. Coordination between the person who first checks that box, the energy consultant, coordination between the next person that gets that CF1R, probably the architect, coordination between the next person that gets it, probably the builder, and the next person who gets it, who's probably the installation contractor bidding on that job, et cetera, et cetera, et cetera. There's a whole chain reaction of things that have to happen in order for QII to pass. Okay. And coordination and communication. You're going to hear me say that over and over again: coordination and communication. The other thing that's important is that the education of the installers is important. The installers need to know what they're supposed to do. Okay. And one of the things I've seen from my many years being out on the job site at the vast majority of the projects I worked on were big production home projects, subdivisions being built. And one of the things I learned is that there's sort of a hierarchy of the trades, right? And very, very low on the hierarchy is the poor people who have to install insulation, especially fiberglass bats and stuff like that. Then when you start getting to spray on foam, they become much more skilled and qualified. Some of the other stuff, but poking in the fiberglass bats. I did that one summer. I helped insulate a house. I worked for a general contractor. It is horrible, miserable work. It is so itchy and miserable. It is just no fun at all. And so these poor people who are doing this for a living um, don't want to be doing it for very long. So they tend to move up the hierarchy. They like to say every insulation installer likes to eventually get promoted to being a ditch digger. That's sorry, that's not very nice, but that's kind of gives you an idea of how miserable it is. Okay, now I've seen some people out there who were great pride in their work, and to watch them work is a real pleasure. But I've also seen people out there, you can tell this is their first day doing it too, and so they just stuff this stuff in there and they have no idea, and so it's very important that they get trained and that they understand the importance of doing that. Okay. Um, HERS raters inspect the installation to make sure that it passed, but it takes a whole chain of people to make sure that it passes, to make sure that it happens correctly in the field. Okay. Now, one
Um,
of the first things. Oh,
Russ, really
yes.
quickly, we got a question on the chat
Oh, yeah.
from George. He
Let's
just
see.
wants clarification as to whether the 2019 CalCerts QII handbook is the one you
Um,
refer to as part of the currently used 2022 code. That is
there
not
should be a
correct, right?
2022 version. There's not a big difference between the 2019 and the 2022 version, but there should be a 2022 version floating around out there somewhere too. So be sure to find that. Yeah. And like I said, they're very, very similar. I think there were just a few little things they changed between the two. But yeah, there should be a 2022 version out there somewhere. Okay, so the first thing that has to happen is and this honestly falls on the architect, is to define the thermal boundary. The thermal boundary, okay? What is the thermal boundary? That seems like such a simple thing. And in most houses it is. If you've got a one-story slab on grade house, the thermal boundary is the walls, the ceiling, and the slab, okay? And that's no big deal. But then we start saying, okay, well, what if it's an encapsulated attic? What if it's a unvented attic with insulation at the roof deck? Now your thermal boundary has been raised up to the roof deck because it's an unvented attic. Well, what if it's a high performance attic? What if it's has insulation at the roof deck, but it's a vented attic? Well, now your thermal boundary's back down at the ceiling again. Okay, so those sorts of decisions have to be made. And when you have a two-story house, it gets a little more complicated. And when you have a raised floor house, it gets a little more complicated too. So we have this very simple little section of a house here. And one of the things you have to define is the thermal boundary. Okay. Now, this is unconditioned attic. Okay. And what defines the thermal boundary are two things: an air barrier and insulation. Okay. Air barrier and insulation. And here's the other weird thing: on horizontal air barriers, okay, um, it is only one air barrier. On vertical boundaries, vertical surfaces, there's two air barriers. The insulation has to be sandwiched between two air barriers. Okay. And so this drawing isn't entirely correct, but the air barrier is basically, in this example, is the sheetrock. Okay. So the horizontal air barrier at the ceiling is the sheetrock, but the insulation goes up above it. But the air barrier is the sheetrock. Now on the walls, the air barrier is the interior sheetrock and whatever's on the outside of the wall. Okay. And now with QII, this was a big deal when QII first came out, is that when you have a knee wall, and a knee wall is any wall that's adjacent to an attic. If you're inside the house and you drill a hole through a wall, okay, and you come out inside an attic, that's a knee wall, okay? And in the old days, all they would do is if you had a knee wall, they would just put the insulation up against it, and if you were lucky, they would strap it in place. Well, now there has to be an air barrier on top of that, either sheetrock or some other air barrier approved material. So you see here, this has an air barrier, okay? Um, Another tricky thing is when you have any kind of a big slide-in tub or shower enclosure, the fiberglass kind that just kind of slide in. All right, there has to be an air barrier behind it. All right, that's a very common fail. And if you look closely in this diagram, you'll see that there is an air barrier behind that. And we have another diagram that I think will show that a little bit better. But um, then the only exception to the vertical surfaces having two air barriers is a rim joist. Okay, a rim joist is that portion of a raised floor that's basically in line with the floor joists. Okay, so think of it as like a belt around the middle of the house. That's the only time you don't need two air barriers. So you can have the outside be the air barrier and then insulation, but you don't need anything on top of that. Now, the interesting thing is that Energy Star, I believe it still does require that there be an air barrier over the rim joists. Okay, and it's kind of a big deal. Um, then you come down. Now you get down to the raised floor. The air barrier then is the subfloor. Okay, the subfloor. The bottom of the floor joist has no air barrier on it, but that's where the insulation extends down to. Okay. So things like knee walls, things like these slide in tub exposure, tub and shower enclosures. And then also places like this. Sometimes these floor joists extend out above the garage. Like if you have a floor above the garage, where is that air barrier? The floor above the garage has to be insulated if there's a room above there. Okay, where does that air barrier stop? And so it has to be continuous throughout the house. So that's very important early on, and it would certainly help. You rarely see this, but it would certainly help if the architect on the sections were to very precisely define the air barrier. Okay. Um, Another big deal that's a requirement of QII is that the top plates have to be sealed. Okay. Now the assumption here is this is an attic above. This is unconditioned space above this diagram, not another floor. Okay, but unconditioned space like an attic. Okay, and the imagine the house is pressurized. Imagine the house is under pressure, because it actually is. It can be under positive or negative pressure just based on wind, based on duct leakage can induce negative pressure. Your ventilation fans, your exhaust fans can induce pressure on a house. Okay. But imagine a house is under a lot of pressure. Imagine you're doing a blower door test on a house and you're pressurizing this house. Okay. How is that air escaping? All right. You want to seal those locations. All right. And one place that a lot of people don't realize is where the sheetrock meets the top plate. Okay. The if this space here is under pressure, that air is going to get into the wall cavity and then squeeze between the top plate and the sheetrock. And how does it get into that wall cavity? Outlets, light switches. It can actually go underneath the sheetrock and get into that wall cavity and then come out here. So that location right there has to be sealed. All right. And it can be caulked, it can be gasketed. There's a lot of different places. Okay. A lot of different ways, methods to seal that. And those are covered in the handbook and other places. All right. But that gets missed a lot. One of the best ways I've seen, I'm just this is kind of a best practice, but it's not the only way. Before they blow in the ceiling insulation, someone will get up in the attic and spray foam all of the top plates. You'll see this like pink or blue kind of a spray foam insulation that seals all those up. Okay. Another place is whenever you have a drop ceiling like this, in order to prevent the insulation from falling down into this area here, you have to put a hard cover over that. So when they blow in the insulation, this hard cover keeps it up at a nice flat level. That hard cover has to be sealed. Okay. When you have two walls that are for some reason butted up against each other, they've double framed a wall, maybe for plumbing, or maybe it's the wall between dwelling units or something like that. But where those two top plate 2x4s meet each other, air can squeeze through there. When you have any kind of duct or vent that passes through the air barrier, this could be sheetrock, this could be sheet metal, okay? That has to be sealed. Also, where it sets on top of the top plate, any kind of masonry that passes through the air barrier of the house has to be caulked and sealed around. Okay. So these are all kind of different locations where the HERS raters are going to go around and look to make sure these were all properly sealed. And if this is a B vent, if this is a hot B vent, um, they have to use fire caulking and things like that too. Okay. So there's different kinds of materials that have to be correctly used. All right. Other penetrations in the top plate can be a plumbing. They drill a hole to run a copper pipe through. They drill a hole to run a waste vent through. They drill a hole to run a wire through. Or there's a knot. There's a knot hole in the wood, and there's just a hole in the wood. Those all have to be sealed. Okay. Not only is that an energy thing, but that's a fire code, smoke spread requirement to seal all these top plates as well. And not just between conditioned and unconditioned space, but even in a two-story house, the mid-level ones have to be sealed too, so that smoke and heat doesn't make it up to the second floor. Okay, so those all have to be sealed. So the HERS rater is going to walk around and seal and check and make sure that. Sorry, they're going to walk. They're HERS rater is not supposed to seal anything, but they're going to walk around and check to make sure that it got sealed. Okay. And then penetrations in the sheetrock, any kind of sealing penetrations in the sheetrock. It's very important that those get sealed. Very common ones around exhaust fans. Okay. You go into a bathroom, you take the cover off the exhaust fan, and you look at there's a metal box, and the sheetrock is cut up to that metal box. That has to be either taped or mudded or caulked or otherwise sealed. There can't be little air gaps around there. um, any electrical boxes in the ceiling that you might see, whether it's a ceiling fan or a light fixture or something like that, those all have to be caulked and sealed around. Fire sprinklers are kind of a sore subject actually. Um, Fire sprinklers, um, because it's a fire thing, it sort of takes precedence over the energy thing. And it really depends on the manufacturers. Okay. So the fire sprinkler manufacturer will tell you whether or not you can seal around those. So always look at the sprinkler manufacturers. So HERS raters, they can't just go out and see a fire sprinkler that's not sealed and go, oh, that's a fail, it doesn't meet QII. They have to go find or ask it to be provided to them the instructions from the fire sprinkler manufacturer to see whether they're allowed to seal around it or not. Okay. In some cases, you are allowed to seal around it, but those are kind of rare, is my understanding. In some cases, you're allowed to build a box over it in the attic side. Okay. And in some cases, you're not allowed to do anything because the way those fire sprinklers work is by getting heat to pass by them so that that little wax thing can melt and it'll turn on the sprinkler. All right. Well, if you seal around it, then there's no air movement around it and it's less likely to go off. Okay. So always read the manufacturer specs. Where I've seen this be a real problem is when an energy consultant takes credit for the house being extra tight and they trigger the blower door test, but then it turns out the house has sprinklers that can't be sealed around and there's no way it's going to pass the blower door test. Okay. But it can pass QII if the fire sprinkler manufacturer specifically says that you're not supposed to seal around those. Okay. Another big one is register boots, sealing around a register boot. So if you take the register, the supply or return grill register off, there's going to be a sheet metal box that's going to be cut through the sheetrock. It's going to penetrate just a little bit into the sheetrock, and that's supposed to be sealed around. Now, one of the common ways to do it is put a piece of tape in there and fold it over that edge. They can put spray foam around the inside. They can spray foam it from the top. They can mud it really good. The sheetrock people can come back and mud around it really good and seal that off. But that is a QII issue. Okay, it can also be a duct leakage issue. How you whether or not you pass the duct leakage test because they tape over the register. And when they tape over the register, any leakage behind the register going up into the attic is counted as duct leakage. All right. So there's multiple reasons why they should tape around there. And man, I've seen some pretty bad stuff. I've taken off supply registers and the hole that they cut, they used a hammer to make the hole. It's like they knocked a hole in the sheetrock with a hammer. So it was all, these round circular holes. And then they just put the register over the top of it. And you could literally put your hand between the register boot and the sheetrock. So that's stuff like that you might see, hopefully not as much anymore. But that's not only is it a leak for duct leakage, it's a leak for the house to leak as well. Okay. And by the way, if I didn't say this already, insulation does not work if air is passing through it. Okay. If you took a sheet of R19 or R21 bats and you made a curtain down the middle of a room with R21 bats and you blew 100-degree air on one side of it, what temperature air comes out the other side? 100-degree air. Okay. Insulation does not filter out the heat. Insulation does not stop convection. The air coming into the insulation is going to come out the other side the same temperature. Okay. The way insulation works is it stops conduction. In order for conduction to stop, you have to have an air barrier that stops the air moving through the insulation. And in a wall, you have to have it on both sides. And the reason is if you don't have an air barrier in contact with both sides of a vertical surface, something happens called stratification or thermal cycles is another name for it. And what happens is, let's say this is the warm side of the house. Okay. It's in the winter time. It's warm in the house and it's cold outside here. Well, this air inside the wall will warm up, it becomes less dense and it rises through the insulation. And then it comes to the top and it comes out and it hits this cold surface. And if there's a way for it to move, it will. It'll drop down. And what it does is it causes just enough pressure for this thermal siphon to happen inside the wall. Okay. And that's enough to reduce the R value of the wall because you're trying to stop conduction, but what is happening is there's actually convection happening inside the wall that's sort of short circuiting the insulation. And the way to stop that is to is to close this gap right here. And so when it's in contact on both sides of the insulation, that's enough resistance to really stop the air from circulating through. It might still do it a tiny, tiny bit, but it's negligible. But as soon as there's a space for the air to move, it'll do that, and that will create enough pressure to cause this thermal siphoning. Okay. And you can see it with an infrared camera. You can see it in a wall. It's very interesting. All right. So that's why a wall has to have insulation on both sides, or sorry, air barrier on both sides of the insulation. But on a vertical surface, or sorry, horizontal surface, that thermal siphoning, there's not that vertical aspect to it that a wall has. You know, a wall have 8 feet of this difference in temperature for the air to cycle through. But when you have a horizontal surface, there's not as much um, pressure driving that thermal siphon on a ceiling or on a floor, raised floor. Okay, so it's only on vertical surfaces that you need this air barrier on both sides. Okay. The other thing that's important, it's an important concept of QII, is what we call six-sided contact. In order to make sure that there's no voids, no gaps, no places for air to move freely, when you put insulation inside of a rectangular shaped cavity, it needs to touch all six sides. Okay. Now, what are those six sides? Well, think of a dice, right? A die has six sides to it. A rectangular cavity also has six sides to it. It has a left side, a right side, a top and a bottom, and a front and a back. So when that insulation goes into that cavity, it has to touch all six of those sides when the sheetrock goes on it. Okay, and so when they put that insulation in there, it's good for that insulation to be sticking out a little bit, so that when they put the sheetrock on there, they know it's making contact. Okay, so six-sided contact is very important. Excuse me, for vertical walls. Okay, another thing is in walls, you have wires and plumbing and stuff like that going through those cavities. All right. How do you deal with that? Well, you've got a pipe running. So this is a slice through a wall. We're looking down from above on this wall. So here's the exterior. Okay. There's whatever the siding is on the outside. Here's your studs. Okay. And you've got a pipe running vertically through this stud bay. And there's a junction box or an outlet box over here too. Now, how do you get that insulation to get in there? There's a couple ways to do it. You can slice the insulation and tuck it in on the left side and tuck it in on the right side. You can trim the insulation and put a little piece of bat behind this junction box. Okay. Notice that whatever little teeny tiny gaps are there are very, very small and they're negligible. Okay. But if you were to just take a piece of insulation and shove it over the top of this pipe, well, the insulation, there's gonna be a big gap behind the pipe, and that's exactly what starts that convective flow. Okay. Another way to do it is you got a pipe or something else running vertically. Okay. Well, if you take fiberglass bats, if you've ever looked at fiberglass bats, you can take it and you can separate it. It's in layers and it's called delaminating. You just put your thumbs in there and you pull it apart and you've got the front half and the back half of the insulation. Well, you tuck the back half in there behind the obstruction, like the pipe or whatever, and then the front half goes over the top of it. That's another way to do it. That is perfectly acceptable. All right. So when a HERS rater goes out and they're walking the project and they're looking at the insulation, and they see this nice insulation all around, well, they know there's wires. They can see outlets and junction boxes around and maybe see plumbing coming out of the top. So they know there's something behind that insulation. So what they need to do is they have to go in and they put their hand behind there and they may pull out some insulation and see to make sure that that insulation goes behind um, the pipe or the wire, whatever it is. Okay. This method here, we call that the cut and butt. So you're cutting it and then you're butting it together at the obstruction. And then this method down here, we call that delaminating. You separate it and you tuck half of it behind and then the other half in front. Both of those are perfectly okay. The whole point of this is to minimize these little tiny gaps. If they're just teeny tiny gaps like that, it's no big deal. But what sometimes you'll see is you'll see a huge gap because they didn't go behind the pipe, or you'll see a big gap here behind the junction box. So that's a fail. Okay. All right. Did we have a question? Let's see. George is asking, sealing at kickboard molding and receptacle, it seems challenging in some cases to stop vertical thermosiphon. Yes, and it's actually you're not sealing those to stop the thermal siphoning. The thermal siphoning is caused when you have a gap between the one of the air barriers and the insulation. Let me go back to this slide here. This gap here is what causes that. Now, what an unsealed, say, junction box or an unsealed bottom plate, what happens there is when the house is under pressure, I'll go back a couple slides, and you start getting insulation, you start getting leakage here. But if you seal these top plates, the pressure, even if air gets inside these walls, it won't escape out the top. So you really have to seal the top is the important part to seal. You don't have to seal around all the junction boxes, okay? But you do have to seal up here. And the reason you're sealing up here is so that any air that does get inside the junction box can't escape through the top here. Now the thermal siphoning is caused by this gap. Okay, it's not caused by a junction box, but it's caused by a gap. And that gap can happen behind a junction box. And that's why the insulation has to get tucked in back behind the junction box. So I hope that helps answer that question. Okay. Some weird things you're going to see is architectural pop outs and other sort of architectural features where they do some weird framing around windows to make them look all fancy and stuff like that. Again, this kind of falls back to defined define your air barrier. Okay. And so again, this is a slice through a wall. And we're looking down on this wall, and this is a window on the front of the house. And they've put these architectural pop outs or bump outs in the wall to sort of frame this window and give it a nice look from the front of the house. Okay. Well, the question is, where is the air barrier? Okay. And there's different ways to define it. All right. And most builders have figured out the cheapest way to define it. Okay. But because so this probably the simplest way to define it is just follow the wall. Ignore the pop outs. Okay. Pretend those pop outs aren't there and just follow the wall. Okay. And there you go. But here's the deal. This is a wall right here. This is a vertical wall. So it needs an air barrier on both sides. This gets missed a lot. You'll see these architectural pop outs, and if you could poke a hole and look through there, you'll see the backside of this insulation. Well, there needs to be an air barrier there. This has to have an air barrier on both sides inside this pop out. Okay. That's a pain in the butt. All right. And so they'll say, okay, well, what if we made this the thermal boundary? Well, then you have to have an air barrier here on the inside of that pop out. And that's like, yeah, that's not worth the trouble. Occasionally, depending on the size and depth of this pop out, just insulate the whole thing. Just fill the thing up with insulation, and then this interior air barrier and this exterior air barrier become your air barriers, and it's not a big deal. Okay. Let's see. Got a question again. Space between sheetrock and insulation is different issue. I understand you say you must seal the top, but not necessarily the junction box. I wonder, is it okay to seal at all junction boxes? I guess a QI plus code issue. Um, QII specifically says that you have to seal where the sheetrock meets the top plate at the top of the wall, and that is sort of the last point that air could possibly escape into the attic. So that's where they want you to seal it. I suppose, theoretically, if you ran around and sealed all of the junction boxes and all of the bottom plates, you wouldn't have to seal the top plate, but that's seems like a lot more work to me actually than just going around sealing the top plate where the sheetrock meets that. So even though it is kind of a possible way to do it, the QII does specifically say you have to seal at the top plate. It does not say you have to seal junction boxes. Now that's assuming, okay, on an exterior wall. Okay. By the way, this brings up an excellent point. I'm glad you brought this up. This ceiling here at the top plate also applies to interior walls. Uninsulated interior walls, you still have to seal where the top plate meets the sheetrock, okay? Because even on an interior wall, air can get inside that wall and find its way into the attic around between the top plate and the sheetrock, okay? I just want to make sure that that was absolutely clear. This problem only occurs typically on exterior walls or only on exterior walls because it's insulated. Okay. This is an exterior wall. This is an exterior wall. These are all exterior walls here. Now, the thing about exterior walls is at the exterior air barrier does have to be sealed. If you have a plumbing penetration, if you have a hole where the Refrigerant lines go out to the condenser. If you have any exterior outlets, if you have any exterior light fixtures, those all do have to be sealed on the outside of the house. Okay, just making sure that that's clear too, because if the inside is of the house is pressurized, it's okay if the air passes through that junction box and gets into the wall, as long as it doesn't go past that exterior wall. It'll stop. It'll eventually stop, and you won't have air moving through that wall, as long as you seal up the outside. Okay, great questions. Okay. Another thing is there's something called full width bats. If you ever walk through Home Depot or Lowe's and you go down the insulation, I always encourage you to do this. Walk through the insulation aisle and look at the packages of insulation. And let's say you have ceiling joists or floor joists is a better example, that are 16 inches on center. Okay. In the old days, I'm not sure if it's still true, but in the old days, you used to be able to buy bats that were 14 and a half inches wide. And that is the 16-inch on center minus the thickness of the framing. So those bats are intended to fit between the framing. Okay. And if you do that and your framing is not as tall as your bats, you get this gap because the bat is only as thick as the space between the framing. And so there's something called a full width bat. If your framing is 16-inch on center or 24-inch on center, your insulation is 16 inches wide or 24 inches wide. All right. And then what happens when your insulation is taller than your framing? It touches. The insulation touches because the width of this bat is the on center spacing between the framing. Okay. And so the bat will expand out and touch each other and cover those framing members. Okay. Um, my next slide is important addendum to this topic right here. Okay. But this primarily applies, this looks like a ceiling. It actually applies more to floors or maybe true rafter ceilings where they're using rafters and not trusses. If these are trusses, this becomes a different issue. Okay. And I'll cover that in my next slide. But other reasons insulation can fail on raised floors is one of the most common floor framing methods in new construction are these TJIs. They're called truss joists. Is a manufacturer's name, but they're just basically a wooden I-beam. Okay, so you see there's a bottom flange, up flange, and this web in the middle. Okay, that makes it a little tricky to get the insulation kind of tucked inside there. Another problem you're going to see is that they don't push the insulation all the way up against the floor joists, and you'll get a gap between the insulation and the floor joists. That is a fail. So on a raised floor house, the HERS rater has to actually put their hand up inside there and feel to make sure that there's no gap between the floor joist and the top of the insulation. That's one way that it fails. Another one is that they don't use full width bats, and there's a gap here on the sides because these I-beams, the middle part is really narrow. Okay. And you get a gap here and you get a gap here. That's a fail. So you have to have a full width bat that the width of the bat is equal to the on center spacing of the framing. And it has to be pushed all the way up and in contact with the subfloor, which is the OSB flooring material up here. Okay. So that's some important, details related to the width of bats and things like that. Okay, now when QII first came out, they sort of turned the head on this and they didn't worry too much about it. But now that QII has been around for a long time, here's the deal. It is basically impossible to pass QII using bats in an attic that has trusses. Okay. That may come as a shock to some people. But unless they do a really, really, really good job, it's almost impossible to avoid gaps and voids because here is a truss. Okay. You've got a bottom chord and then you got some diagonals coming up all over the place. Okay. Well, those are 2 inch and a half wide. They're 2 by material. Okay. And when you take bats and you put it around 2 by material, it's impossible to not have gaps. Okay. Well, not entirely impossible. How would you avoid these gaps? You'd have to actually trim these bats. Nobody is going to do that. Nobody is going to trim the bats so there's no gaps here. Okay. The other problem, this gap here would be right up here. Okay. But what you don't see is down here, there's also a void or a gap all along these 2x materials. So technically speaking, it is impossible without a lot of effort um, to pass QII with fiberglass bats in an attic with trusses. Okay. Now, if it's a true rafter ceiling where instead of trusses, they're using 2x rafters like 2x10s or 2x12 rafters, and they don't have these diagonal pieces coming up out of, which is very rare in California new construction. Okay. So how do you fix this? All right. So if you have a situation where you're a HERS rating, you go out and you check, you're like, oh shoot, they use bats in a truss attic. Uh-oh, I gotta fail this. How do you fix this? You can blow in insulation over the top of this. Okay, that is an acceptable. It won't get rid of these so much, but by adding that extra R value and covering these gaps of here, that can do it. Okay. The easiest way to pass QII with a rafter ceiling is blown in, loose fill blown in. Okay, just loose fill blown in, cellulose, fiberglass, whatever. And what it does is it all fills around all these things. Okay, so very very difficult to do that. All right, so just be aware of that. Okay, so getting back to the topic of coordination, coordination and communication. I put together this matrix a long time ago, and it has really stood the test of time. And what I did is I said, okay, who is involved in making sure a house meets QII? Who's responsible? Who has some impact on making QII? And I just listed them out. So okay, the energy consultant, they start the process. They're the ones who say this house needs QII. The builder and the architect say, yeah, all right, that's what we're going to do. We're going to build the house that way. The HERS rater certainly is involved. They have to inspect everything. The insulation installer is certainly involved. They have to install the insulation well. The framer, because they may be the ones who have to frame it so that you can put an air barrier on the outside of a, say, let's say a knee wall or something like that. The framer has to make sure that drop ceilings get a hard cover over them, things like that. So the framer is certainly installed. The drywall installer, they're the ones who have to make sure that, or they're one of the ones who have to make sure that the drywall is sealed to the top plate. So they certainly have a play in it. And then all the other miscellaneous trades, the electrician has to seal around the wires, or it has to make sure the wires get sealed around. Somebody's got to do it. The HVAC contractor, someone's got to seal around the register boots. The plumber, someone needs to seal around all the plumbing penetrations. So all pretty much all of the trades, everybody but maybe the painter and the concrete person, I don't know, need have some say in it. Okay, so we have all these miscellaneous trades. So here's all the people that play some role in making sure that QII uh, passes. Okay, and then I said, okay, what are all the different stages of construction? What happens? What are the different points in time during the construction of a house? And these aren't standard. These are kind of typical to what you'll see in like a subdivision. All right, they'll do pre-design where they do preliminary designs on the house, and then they'll finalize those designs, and then they may have they used to call them value engineering meetings. Now they call them trade review or trade coordination meetings, where they all come in and people have a say. And then they start building the house. They'll start grading, then they'll start framing, then they'll do rough in of HVAC and plumbing and stuff like that. Then they insulate, then they do the drywall, then they do all the finish work, and then they have the final inspection. Okay. Again, these are not standard. People will split this up differently and call them different things, but this gives you a rough idea of the process. Okay. So you've got this matrix. You've got all the people involved and all the different stages of construction. And anywhere in this matrix that you see text means that somebody's got to do something. Okay. There's a lot of these squares have text in them. Okay. So as an example, At pre-design, the energy consultant specifies QII. At design, the energy consultant may participate in a kickoff meeting and make some comments and say, okay, here's your preliminary Title 24 reports, and then they may finalize it later on. Okay. The builder will approve the energy features. They'll have a kickoff meeting. They'll sign the CF1R. The HERS rater hopefully gets to participate in the kickoff meeting, hopefully gets to review the plans ahead of time. And then they start coordinating with the trades. Then they start doing their inspections. Then they do their final inspection. The installation installer hopefully has some participation in the kickoff meetings. They will say, okay, yes, they will hopefully bid the project, assuming QII. Okay. They understand the QII. They'll do the pre-installation stuff. Then they start installing bats and other insulation and loose fill. Then they fill out their CF2Rs and so on and so on. Okay. So there's a flow of information that has to happen, and it starts up here with the energy consultant. So the energy consultant specifies QII. At the very least, the energy consultant needs to tell the builder and the HERS rater that this project needs QII. Now, back in the day when QII was an extra credit, this was super, super important because if they didn't tell anybody, they would assume that it wasn't going to happen. Nowadays, most houses have it. So this isn't quite as important. Okay. Most people just kind of assume QII is on the house nowadays, maybe in most parts of the state. But then this other stuff, the HERS rater has to make sure that these people someone needs to make sure that all these people down here understand what their requirements are. The HERS rater is a good person to do that. It's usually not their first rodeo. They've been through this before. They can say, "Oh gosh, man, I had this project where this was an absolute nightmare. Let's please make sure this doesn't happen on this project." And so they can give you a lot of advice on the front end of a project. And I really encourage that HERS raters be given the opportunity to do that. All right. Contact your HERS rater as early as possible. Let them review the plans. Let them point out any potential issues that might happen with the plans. And then all this coordination has to happen in order for all of these to pass at the end. Okay. If you don't do that, if you don't do that, here's what happens. The energy consultant checks the QII box. They give it to the architect. The architect says, okay, whatever. And then no more coordination happens after that point. The HERS rater comes out there, does their inspection, and it fails. And they say, oh, crap, we failed. What do we do? What do we do? When QII first came out, when it first came out, I was probably getting 3 or 4 phone calls a day from HERS raters, certainly at least a week. I was getting at least one a day from HERS raters going, hey man, I'm out at this project and I'm inspecting QII and I came out here and they've already sheetrocked. What do I do? And the answer is easy. You fail it. That's a fail. You just say, sorry, you failed QII. I can't, if I can't see it, I can't inspect it. And they'll say, "Oh, can't you get an infrared camera or something? Or, what if I took pictures and what if I had pictures of it all looking good?" No, that's not what the protocols say. There is no process for doing infrared cameras and stuff like that. The HERS rater has to see the insulation before it gets sheetrock. So and before the insulation goes on, they have to see the air barrier. Okay, I've had HERS raters even to this day. They'll call me and say, "Hey, they've already insulated, but I wasn't able to see the air barrier. What do I do?" And I said, well, you're gonna have to feel around behind all that insulation. It's gonna take you a lot longer to do that inspection because you got to make sure there's an air barrier behind all that insulation. And so it's better if the HERS rater comes out before the insulation is installed, inspects the air barrier. In fact, this is how the forms are designed to work. Okay. The ENV 21 and 22, I think there's just 2 of them now. Um, there's one for inspecting the air barrier, and then there's another form for a separate visit for inspecting the insulation itself. Okay. So very important that this coordination happen. Okay. Very important that this coordination happen. When Gina Rod and I teach the QII class, for builders and architects, we tell them take these forms, take the forms that the HERS rater is going to use to inspect it, go through it and assign each item on that form to a trade. See, okay, insulation contractor, you're going to seal all these penetrations. HVAC contractor, you're going to seal all these penetrations. Sheetrocker, contractor, you're going to seal at the top plates, and on and on. Make sure all of those items are specifically assigned to a trade so that there's no finger pointings. When the HERS rater gets out there and goes, "Hey, all these things they haven't been sealed yet," and the installation guys, "Oh, that's them over there," and those people go, "No, no, that's those folks over there are supposed to do that," and you start getting a whole bunch of finger pointing, and it becomes an absolute nightmare. So that's on the builder. Okay, this class is specifically for energy consultants, so we're kind of focusing on that responsibility. Okay, so and speaking of builders, here are some tips. These are tips that an energy consultant can give to their builder. Hey, and help make things go along. Because the last thing an energy consultant wants is to get the phone call from the builder saying, "Hey, we didn't pass QII. We need you to rerun the calcs without QII," and now all that pressure is on your shoulders to make that work, and you're going to end up being the bearer of bad news that they're going to have to spend thousands and thousands of dollars on additional features to do that. Okay, so builders, evaluate the plans very carefully. Look for unclear parts of the thermal boundary, knee walls, hard covers, bump outs, fireplaces, anything that's not just a plain wall meeting a plain floor meeting a plain ceiling, anything that's unusual. Define the air barrier. Okay. Decide exactly where that thermal boundary is going to be. Precisely defined responsibilities for the trades. This is what we say. Get those forms, the forms that the HERS rater fills out. It's like a giant checklist. Go down that checklist and say, okay, this is responsibility of this trade, this is responsibility of that trade, this is and assign those. Make sure that's in your contracts for crying out loud. Okay. Blocking attic vents, ceiling around fans, electrical boxes, all that stuff needs to be handled by somebody. Contact the HERS rater. Say, hey, HERS rater, give me your checklist. What checklist do you, when you come out and inspect for QIA, what do you use? Can we please use those checklists? Okay. Any other informational materials? The QII handbook. Okay. Meet at the project early. Have the HERS rater walk through the sales models and stuff like that and go, oh, that's going to be an issue. Oh, you see that? You see that fiberglass tub and shower insert up against an exterior wall? That's going to be a problem. Do you see this jacuzzi tub that's up on a platform that's up against an exterior wall? Guess what? Underneath that platform has to have an air barrier and insulation against the exterior wall. Things like that. Okay. Meet at the project early, walk through it. Learn to use the HERS registry. Okay. This says CalCert registry. Obviously, they're not around anymore. So now it's Cheers. Learn to use the Cheers registry. That's where all the forms get filled out. That's where they all get signed. Learn to use it. Okay. All right. Here's some examples from the CalCert's QII handbook. Okay. It's basically a condensed version of RA 3.5 with pictures and diagrams. It's about 116 pages. I want to say the last version that I saw, and it does say 2022, I want to say it was more like 130 pages. It got a little bit longer over the years. If there's any conflict between this handbook and the protocols always take precedence. They are the code. It was updated for 2022. It's downloaded for CalSTR's website. The CalSTR isn't around anymore, so it's floating around. It's floating around. Okay, some important things to make note of: draft stops, and hardcovers. The idea is if you go up into an attic and you look across that attic, you want it to be as flat and smooth as possible. Some architects like to drop ceilings. They like to have vaulted ceilings. Like to have all these different ceiling levels and bump outs and coppered ceilings and archways and all this crazy stuff. Okay. Well, the problem is when you blow in insulation, the insulation is going to fall down to the lowest level. Okay. So if you have a place where like a hallway is a foot lower than the room next to it, okay, you either have to insulate all the way around the perimeter of that drop, or you put a hard cover over the top of it and blow the insulation so that it's nice, flat, and level. That's the better way to do it because there's less surface area that way. All right, but it just has to have a hard cover. And then anytime you have ducts or vents or anything going through a chase, you've got to seal around those. And you can see here that they put in a draft stop, but they didn't seal the corners. So that would be a fail. So this would be a pass down here. This would be a pass because you can see they use caulk and stuff like that. Okay. Defining your air barrier. If your insulation is at the roof decking and it's an unvented attic, okay, now your air barrier is the roofing material or the roof deck. Um, if it's an encapsulated crawl space, an unvented crawl space, now your air barrier drops down to the dirt. Okay. Oh, here's a good example of when that those tub and shower enclosures, if you were to slide that back, okay, if there's no air barrier behind it, now that fiberglass tub enclosure is actually the thermal boundary. Well, that's not going to work. Okay, there's a gap and stuff like that. Okay. Spray on foam. Spray on foam is becoming much more popular. Um, spray on foam does two things. It insulates and it seals. Now you have to look at the type of insulation, the type of spray on foam. There's two kinds, generically called open cell and closed cell. Some call it high density, medium density, low density, but open cell and closed cell are the generic terms. Okay. They have different sealing properties and different R value properties. Okay. So in order to be considered a seal, closed cell has to be at least 2 inches thick. So in order to seal any leakage here, you need at least 2 inches of insulation to do that. Okay. So in order to be a seal, it has to have a certain thickness. For open cell, it's 5.5 inches. That's quite a bit. Okay. It's 5.5 inches in order for this to be considered an air sealant to prevent air from passing through it and and escaping through a crack or a hole in the wall or something like that. All right. Now that's one thing. That's the sealing. Now the other part is the R value. The R value, the thickness of the insulation has to be thick enough to meet the R value as specified. And sometimes that thickness is not as thick as the framing. So this is a 2x4 framing. Maybe to meet the R value, it doesn't have to be 3.5 inches deep. And so what happens is you get a void here. Well, guess what? With spray on foam, that void is okay because remember the reason we don't want that void is because if you have that gap, it will cause a thermal siphon. Well, that's in bats. That's in fiberglass bats. With spray on foam, the foam is dense enough that it won't do that thermal siphoning. So you don't have to worry about the voids. And what you'll see very often is they'll spray it on and then they'll take a big blade and they'll shim it off at the thickness of the framing. And if there's voids in the middle, those voids are okay as long as they're at least 2 inches away from the edge for closed cell and at least 5.5 inches away from the edge for open cell. Okay. And then the thickness has to meet the R value. Where the void is, where it's the least thick, you can take a coat hanger or any kind of metal rod, poke it in there, put your thumb over where it touches the insulation, pull it out, and measure that thickness, and it has to meet the R value. Okay. Now, for spray on polyurethane foam, there's some generic R values that you can use, and we'll talk about that more in just a second. Okay. Attic venting is very important. This is another thing that HERS raters check for, is to make sure before any blown in insulation gets installed, is that there are attic baffles to allow the air to come in through any sort of vent and move between the insulation and the attic. So that allows it to be vented. It's attic venting. That's something that has to be checked. IC rated can lights is something else HERS raters will check for to make sure that the can lights that are installed can actually be covered with insulation and that they're airtight. It's AT and IC rated. That's all mentioned in the handbook. Any sort of weird corners where the framing creates a void on the outside, those have to be pre-insulated before the exterior sheathing goes on. Okay. Here's that jacuzzi tub I mentioned. This one had this was interesting. This house had a jacuzzi tub, and the access for the motor to service the motor for the jacuzzi tub was on the outside of the house. There was a metal door on the outside of the house that you had to open up, look inside, and you could reach the jacuzzi tub motor to service it. Well, that door had to be insulated. Okay. They had to make sure they insulated that door. And then the wall next to it needed insulation and an air barrier on top of it. Okay. So just a lot of little details like that are needed in order to pass. This tub being pushed up against this wall, they better hope that behind this tub there's an air barrier, sheetrock or something else covering that insulation. If you can pull this tub out and see insulation like you're seeing right here, that would be a fail because there's no air barrier behind that. All right, it has to be in contact with the insulation. Okay. Skylight wells have to be insulated, and because they're considered a vertical surface, they need an air barrier on both sides of the skylight well. If the insulation is up at the roof deck, spray on foam up at the roof deck, okay, not as big of a deal, but now your air barrier is up here, but you also need this air barrier over here, okay. Um, Headers, my least favorite subject, insulated headers. Um, Headers are supposed to be insulated, okay. If you have rigid foam insulation on the outside of your house, just because that's what was called out, that's adequate insulation on the headers. But if you don't have that, you need to have additional insulation on the headers. This has caused big projects to fail because they didn't have insulated headers. And I think that's kind of a shame because if you think about how much area is that in a house, the headers on an exterior wall, how much area is that? It's not a whole lot of area. And all we're talking about is a difference of R3 for that area. That's not a lot of heat loss. And I hate to see a project fail because of that one thing. Um, but insulated headers, this is one of those things that you need to talk to the builder and say, hey, you're not putting rigid foam insulation on the outside of the house, therefore your headers need to be insulated. Okay. And how that insulation happens is the header will have to be narrower than the framing, and there has to be you know, a space to put some sort of rigid foam insulation on the inside. And for 2x4 walls, it has to be R3, and for 2x6 walls, it has to be R5. Okay. This is a detail that can cause a lot of issues if it's not called out in advance. So HERS raters, this should be one of the first things you talk to the builder about. Hey, are you going to insulate those headers? And if they say, well, we weren't planning on it, but we're having insulation on the exterior wall, oh, then that's fine. If you have a rigid insulation on the outside, that's going to go over those headers, and that counts as the header insulation. But if they're just doing insulation in the framing alone, then there has to be extra insulation on those headers. Okay. I talked to a structural engineer friend of mine, and I said, do headers always have to be the same thickness as the framing of the wall? In other words, if you have a 2x4 wall, do the headers always have to be 3.5 inches thick? And he said, no, the only reason we do that is because it's easier to install that way. They don't have to be that thick. So the structural engineer has to specify that the header can be narrower than 3.5 inches to allow them to put the rigid foam insulation. If you look really closely at this diagram here, you'll notice that the header is not as wide as the wall is, so that there's space to put that R3 insulation in there. Okay. That's a that's a real pain in the butt. Okay. So make sure that gets called out early on. Again, that's the framer's responsibility. Unvented attics, make sure any gable ends get insulated. Okay. Make sure that that's called out on the CF1R too. A lot of times energy consultants forget to model that exterior wall, that gable end, because the insulation is up at the roof deck. So that wall needs to be insulated, usually at the same insulation level as the walls below it, the exterior walls, but maybe not. Okay. So maybe it may not have the rigid foam insulation on the outside or something. Here's this was a builder in Las Vegas actually that would actually hang this fabric and fill the fabric with insulation. So it was kind of a loose filled insulated attic. It was really interesting. Typically what you'll see these days though is spray on foam. Well, for insulating the attic. Okay. At the very end of the QII handbook is a checklist. We took the ENV 21, turned it into a checklist. We took the ENV 22, turned that into a checklist. There's another document at the end of the QII handbook called How to Read the Insulation Requirements of a CF1R Perf 01. For you energy consultants, you're used to looking at CF1R perfo ones, and they can be 12, 14, 16. I've seen 25-page CF1Rs before on a big house. Okay. That's a lot of pages. And if you thumb through it, you're like, what is this stuff? This doesn't make any sense. So now you hand that to an insulation contractor and you say, here's your requirements to insulate this house. And they're going to go, what am I looking at here? There's all this weird, what is this? Energy ratings and all this other stuff. So what we did is we came up with a document, how to read the CF1R specifically to find the insulation requirements. So we say, go to the opaque surfaces, look at this, and then look at the opaque constructions and look at the assemblies, look at this stuff here, and this will tell you what you need to do. So that's a very useful training tool for insulation contractors. Okay. All right. So some other kind of odd things. I mentioned earlier for spray on foam, if it's open cell or closed cell, there's these generic R value per inch numbers that you can use, but some manufacturers have better numbers than those. Okay. If you choose to use a better R value per inch when you model spray on foam, that triggers a special requirement. Okay. The HERS rater has to go out and make sure that it meets the right thickness. Okay, and that the right insulation material got installed. And they have to have some sort of OEM manufacturer's spec sheets to verify it. Okay, so there's some additional things that has an extra checkbox on the checklist too. All right. How are you? Oh my goodness, we're right at 11 o'clock. Sorry, Danica, I didn't give you much time. I really appreciated the leisurely pace of this class. Like I said, this was normally a 1 hour class, and we had an hour and a half to do it, so I was able to give you a lot of extra advice. And look at that, I took almost every single minute I was allotted. Danica has a couple slides to finish up, and
Yeah.
if there are any additional questions, please drop them in the chat.
Yeah, thank you, Russ. Good thing we scheduled this up to 11. But yeah, I as we wrap up, actually, I will launch our survey. Let us know your thoughts and what other improvements and courses we should offer in the future. And if you have any Energy Code or CalGreen questions, we have a Code Coach program to answer those questions for you. Otherwise, if you have any questions in receiving your AIA or ICC units, please reach out to my email listed on the slide. And in the next couple of days, you will be receiving your AI, you will be receiving the slide deck and a link to the recording. And just an FYI, the 3C Run offers a free HERS Rater and EPA 608 certification training for those who are non-SoCal Gas customers within the Tri-County region. And there's also an option if you are a SoCal Gas customer. And I'd like to invite everyone to our other upcoming courses next month. We have an in-person course on passive solar on August 12th and a CalGreen webinar on the 13th and a lot more. And you can see these trainings and sign up for it on our website at 3c-ren.org. And with that, I'll pass it back to Russ if there's any last minute questions. And yeah, I'll keep this open so that people can um, fill the fill in the survey. And yeah,
Awesome. If anyone has any more questions, feel free to drop those into the chat. There's one. Can these trainings be applied to? Oh, I don't know what that is. That's a Danica question.
um, to see certified passive house design and training professional development requirements. Um, yeah, I'm not sure, but I will get back to you on that, George. I'll ask Passive House Network specifically, and I'll get back to you.
Sometimes you just have to submit the curriculum to those organizations and they just approve it or not. Um, but sometimes like AIA, you have to pre-submit your curriculum and then they pre-approve it for AIA to
Yeah,
use. I'm not sure if Passive House is quite that strict or not.
yeah, I'm not sure about Passive House either, but I can reach out.
May I ask another question before you wrap up?
Yeah.
Yes.
Um, Russ, thanks so much for great training. I noticed you mentioned CalCerts and you mentioned Cheers. And in some cases, some things about CalCerts are now replaced by Cheers. You mentioned that you're redoing the CalCerts handbook. Is the final version of that that you're revising, is that going to be a Cheers handbook that we can all cheer on, or is that going to be a CalCerts?
Great question. Actually, neither. It's going to be an Energy Code ACE document. Yeah, Energy Code ACE is sponsoring the rewriting of it, and they will provide it just like they provide all their other wonderful materials that they provide on their website. You know, all their fact sheets and trigger sheets and all that good stuff. It'll just get added to all that. Yeah, yeah.
Right.
Question on the header insulation: what exterior siding counts as R3 R5? OSB or must it be rigid? It's the rigid foam. So a lot of times houses, maybe it's not quite as common in the 3C rent territory, but certainly in the Central Valley, you know, they'll do a 2x4 wall with R21 in it, and then they'll do an R4 or R5 rigid and do the stuck insulating material in order to count as the header insulation on the outside. Yeah. Yeah. I've actually seen a house. I mean, they failed QII. They failed QII, and they came back and they actually put a piece of rigid foam insulation and stuccoed over it. They were actually able to disguise it so that it kind of looked kind of nice. I mean, it had a little bump out above the windows, but they were very lucky that it turned out looking nice. Otherwise, it could have looked really, really dumb to have this little, you know, 3/4 of an inch bump out in the stucco above these windows for the insulation. I've heard of people doing it on the inside, you know, but it can be a real nightmare. Like I said, in the grand scheme of things, there's just so little heat passing through those headers to begin with that that little bit of extra insulation, I really wish, and I actually requested this a couple code cycles ago. I wish the software had a little box that you could say, I'm doing QII, but I'm choosing not to insulate my headers, and I'll take the penalty for that. And then they just figure out how many windows, how wide they are, and they can calculate a little UA delta T. And I guarantee you it's going to have a tiny impact on the conductive heat losses of that house. But what that does is it gives them the option to not have to worry about those silly, and I shouldn't say silly, those darn insulation headers on the insulation. So yeah. Zip System makes R6 insulated sheeting now that's really nice for monopoly building. Yeah, absolutely. Yep.
And I think we are over time, so thank you everyone for coming, and thank you, Russ, for delivering a great presentation on QII. Thank you so much, everyone, and have a great day.
Thank you.